Hello everyone and welcome back to the General Chemistry Laboratory. We today are going to finish our discussion on gravimetric analysis for sulfate, and I would like to start by reminding you what happened in the video that I posted for the first week of this experiment. We are now discussing second and last portion of this experiment. So last time I took known amount of tetramine copper sulfate monohydrate, the purple solid that was prepared earlier. I dissolved it in water and I added some hydrochloric acid. The result is substance dissolved and dissociated, and one of the ions produced was sulfate ion. I then heated the solution until it was very hot, almost boiling. And then I added barium chloride, which was used as a source of barium ions. Barium ions from barium chloride reacted with my sulfate from the carbonation compound and produced white precipitate of barium sulfate. Because barium was used in excess, we're assuming that sulfate is a limiting reactant, and therefore we can tie the amount of barium sulfate that's produced to the amount of sulfate that we started with in our solution. So today, our procedure will involve filtering barium sulfate. We're going to use gravity filtration because gravity filtration, albeit slower, produces better results, much more accurate determination, because we're trying not to lose literally any single particle of barium sulfate. And so we're going to filter it, and then we're going to burn off the filter paper in the second portion of the procedure using a heat-resistant container called a crucible. I will show it to you shortly. And then the calculations involved would have you measure mass of barium sulfate obtained after filter paper is completely burnt off, converting it to moles of barium sulfate. Of course, you would have to figure out molar mass of barium sulfate, and then from moles of barium sulfate, you would have to find moles of sulfate, which is easy because it's 1-to-1 ratio. 1 mole of barium sulfate contains 1 mole of sulfate. And then, knowing molar mass of just SO4 minus your sulfate, you can find its grams. And once you have grams of sulfate, you can find mass percent sulfate in your purple coordination compound. I would like to ask you to take a look at data sheet number 3 in your lab manual. I'm going to find it here real quick. Everything I just described in terms of the stoichiometry and the calculations you have to do, you will find all the equations on page 94 of your lab manual. And then on data sheet 3, which is on page 103, you will have mass of purple solid, and then you will have mass of barium sulfate provided to you. So you will have the first entry and entry number 4 on your data sheet. It says weight of barium sulfate. And then you're going to have to calculate percent sulfate on coordination compound. And so I'd like to point out that to find percent of sulfate in coordination compound, you would take, you would have to find mass of sulfate, and then you would divide it by mass of purple solid that experiment was started with. All the numerical values will be provided by your TAs later. And I would also like to talk about final calculations you will have to do to complete this big experiment. Some data you already have for it, some data you don't yet, but you will soon. So I'd like you to find page 98 in your lab manual. And what this page explains is how to find the empirical formula of the purple coordination compound. So up on the screen here, it says page 43. In fact, this should be page 98, not 43. I apologize for that. So let's briefly talk about finding the empirical formula. So percent copper that you need to know was found on data sheet number 2. So like I told you before, if you email your data sheet 2 with your calibration graph to me, I will take a look at it and I will let you know if there are any issues with it. So copper, mass percent copper is found on data sheet 2. Mass percent sulfate is found on data sheet 3. Percent water is given to you on page 98. Again, it's not 47, it's page 98. And on that page, it tells you that mass percent water is 7.3%. I'd like to point out that I will post these notes on Canvas under modules. So look under modules, you will see these notes posted, so you can use these as a guide if you'd like. Although again, this information here is given on page 98 in your lab manual. And then once you have 3 out of 4 components of our purple coordination compound, you can find percent ammonia. And percent ammonia is found as by difference, by taking 100% and subtracting the sum of copper, sulfate, and water percentages from 100. So that will give you mass percent ammonia, and then you can use these mass percentages, 2 of which, these first 2, I experimentally found, and you can use these percentages to find the empirical formula. Now, I'd like to point out that if you need help and if you need sort of a reminder of how to use mass percentages of components to find empirical formula of the compound, I did include an example in your lab manual. So if you'd like, you can take a look at page 85. Example 1 will tell you how to convert mass percentages into empirical formula. The calculation for empirical formula should be entered onto data sheet number 1. So let's quickly review as far as data sheets are concerned. So data sheet 1, which is page 100, will include mass percentages of sulfate and copper and ammonia, and you will also enter the empirical formula, and then you will show how you found the empirical formula on the bottom of data sheet 1. I left enough room, I hope, for you to do these calculations. And then data sheet 2 is what we discussed before break, and I do expect you to be able to find concentration of copper from your graph, mass of copper and percent copper, and fill out this data sheet completely. And then data sheet 3 is where you will be filling out data that you don't have because you weren't able to do this experiment, but will be the data will be mailed to you, and it will have weight of purple solid, and it will have weight of barium sulfate. And then you're going to have to convert mass of barium sulfate, the weight of barium sulfate, to moles of barium sulfate, and then moles of sulfate, and then grams of sulfate, and then find mass percent sulfate in the purple compound. Your assignment for next week is to complete all 3 data sheets, including empirical formula calculation, and you also have a final report that you must complete. That's page 111. All these pages, along with the calibration graph, will have to be either scanned or taken a picture of and sent to your TA for grading. I'd like to point out that when you're taking a picture, if you're not able to use a scanner, please make sure that picture is taken in high resolution so that TAs are able to print it and grade it and it's legible. So now we can talk about the procedure. If you recall, we left off last time where I heated my solution. I added dropwise my barium chloride. It caused the precipitation of barium sulfate. So hopefully you can see this white precipitate on the bottom here. So our today's procedure will cover filtration of barium sulfate. And then in a later video, we will show you how this barium sulfate can be weighed after the filter paper used to hold it during filtration is burnt off. So what I have here is filter paper This is a circle that will fit in a glass funnel, which I hopefully have here. Yes, I do. So what we need for this portion of the procedure is special filter paper. This is a wire triangle that I place on top of my ring holder to accommodate my funnel, so the funnel is held safely without me having to hold it. And first I'm going to fold the paper to fit the funnel. And I'd like to point out that this filter paper is special because it's called ashless. When it burns off, it does not leave any solid residue. So I'm going to fold the paper in half like this, and then not quite in quarters, making one quarter slightly larger in size than the other. Hopefully you can see here, this outer quarter is a little smaller in size than this inner quarter. And then I'm going to tear off the corner that I'm holding right here, portion of the smaller quarter, the corner here. I'm going to save it, and I'm going to show to you later what I need this for. And then I'm going to open the paper where a larger quarter was, so you can hopefully see it creates a cone. And this cone will fit nicely into my funnel. As you can see, when I place the filter paper in the funnel, the paper covers the funnel completely. You almost cannot see any glass. That's how it should look like. So we're going to set the funnel in a triangle, and you'll notice paper sort of trying to jump out. So what I'm going to do is I'm going to place a beaker underneath the funnel to collect the waste. I'm going to lower the ring holder a little bit to prevent splashing, and then I'm going to sprinkle some deionized water on my paper. Once the paper becomes wet, it will not jump out anymore. It will stick to the glass a lot better. So now I'm ready to start filtering. As you can maybe see, there's some moisture accumulated on the beaker. Because beaker was hot, I covered it with a watch glass. So what I'm going to do is I'm going to hold the watch glass above the beaker, and I'm going to use my wash bottle to sort of wash down this liquid, because that liquid might contain some of the barium sulfate. So I don't want to lose literally any of the barium sulfate. So I washed it down. And then I'm ready to start filtering, but before I do, I want to make sure my precipitation is complete. We talked about this earlier, that barium chloride was added in excess, so it's not likely that I have any sulfate ions still present in this liquid above my precipitate, but it's still worth checking. So what I'm going to do is I'm going to take a pipette, and I'm going to add a little bit of barium chloride dropwise. I'm going to watch what happens in the supernatant, or the liquid above the precipitate. The liquid right now is pretty clear, and when I add barium chloride, I'm not expecting to see any additional precipitation. So the liquid above the precipitate should remain clear, indicating that all of the sulfate has been converted into water-insoluble precipitate, which is my barium sulfate. As you can see, this indeed is the case. I added a pipette full of barium chloride, and I did not cause any additional precipitation, which I did not expect to happen anyway, because I already added a fairly large excess of barium chloride. So now we can go ahead and start filtering. I'm going to turn this around so you can see it a little better. And I'm also going to quickly put a larger beaker underneath my funnel to ensure I have enough room for my filtrate. Now, when filtering, what I want to do is I want to make sure the liquid actually carries the precipitate with it as it's being poured into the funnel. So I'm going to agitate my precipitate. I'm creating a suspension, a mixture of solid and liquid, where solid is not soluble in a liquid. And so now I'm going to pour using my stirring rod to prevent spilling. I'm going to pour some of this mixture through and start my filtration. I'm going to stop the video for now because it's going to be a long process, and I want to shorten the duration of the video, and we'll come back shortly.